Okay, let's take a look at section 3.2. And section 3.2 gets into another type of function called polynomial functions. We did quadratics in the last section, and quadratics are actually a certain type of polynomial function with degree 2 because the highest power is 2. That's x squared is when we dealt with quadratics. But this time we're going to look at polynomials that have higher degree than just 2. So in the guided notes, follow along with me here. The first part, it says the definition of a polynomial function. There's a very formal definition for this in the book. I'm just going to write a little of it here. You don't have to have this memorized or anything like that. I just want you to see what we're talking about or have some idea of what it looks like. So it's a function. I'm going to use f of x as the notation. Of course, y would be the same thing. So we would have the first term would be ax to the n, where n would be the highest powered term. A is the leading coefficient. That's the coefficient on that term. And then the next term would be something, I'm going to call it a sub n minus 1 for the coefficient x to the n minus 1. So they would go down in descending order. That's usually how they're written. Plus or minus dot, 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 and then some constant term at the end. So a polynomial may have just one term. It may have 10 terms. It just depends. Poly, of course, the root word poly means many. And so because it could have many terms, that's why they're called this. So a is the leading coefficient of it's the term on the high, or the coefficient on the variable with the highest power, called the leading coefficient. N is the exponent. I actually prefer the word degree, so I'm going to change this instead of exponent. I'm going to call it degree. So degree is, if you want to make a note, that's your highest exponent. Okay, so whatever your exponent is that's highest, that's going to be the degree of the polynomial. So some examples of some functions, I'm just going to give you a few here. So we could have something like negative 5x to the 7th plus 3x to the 4th minus x squared plus 3. That might be an example of a polynomial. It can have one term. So it could be like g of x equals 6x to the 4th power. That would be a monomial, but it would still be under the umbrella of polynomials. Like I said, quadratics are also polynomials, so something like 3x squared plus 2x minus 4. That's a quadratic, but it's still under the branch of polynomials. Some features of graphs of polynomials is that they are smooth. There's never any cusps or corners or sharp edges in a polynomial graph, and they're also continuous, meaning there's no breaks, there's no asymptotes, there's no holes. They're very, very smooth, nice, well-behaved functions. So they're some of the easiest ones to graph and the easiest ones to work with in higher level math. So one thing I want you to get good at is knowing what the end behavior is for a polynomial. And so what we're going to do to figure that out is we're going to use something called the leading coefficient test. And so make a note that this is the end behavior. So if you're ever asked about end behavior, this is the way we're going to do it. So there's two things you want to look at. You want to look at the exponent, and again, I like the word degree better, so I'm going to cross this out and change it to degree. So whatever the highest power term is, that degree. If it's odd and the leading coefficient is positive, okay, so if a is positive and the degree is odd, then the end behavior is going to do opposite things. The word odd starts with an O, that's how I remember opposite. And what's it going to do? It's going to fall on the left and rise on the right. And if we were to look at a drawing of it, fall on the left, rise on the right. Now we're only talking about the end behavior. There's other stuff happening in between here, but we're just talking about the end behavior. So when you have an odd degree and a positive leading coefficient, it's going to fall on the left, rise on the right. Now, if we have an odd degree but a negative leading coefficient, odd means opposite still, but now the leading coefficient is negative, so it's going to cause the graph to reflect over the x-axis. So instead of falling on the left, it's going to rise on the left and fall on the right. So it's going to be very similar, like I said, in terms of it's going to be opposite, but it's going to rise on the left, fall on the right, just like that. Again, we don't know what's happening in between. Other stuff's going to figure out what's happening, help us figure out what's happening in between. All we're talking about right now is the end behavior. Okay, if the degree is even and the leading coefficient is positive. So when I think even, I think sameness, nice, even things, same thing is happening. If the leading coefficient is positive, it's going to rise on the left and rise on the right. So rise on the left and rise on the right. A parabola would have actually been an example of this. Think about a parabola would have an even degree. The highest power would be 2. And if that leading coefficient was positive, remember we said it goes up on both sides. It makes the U shape that opens up. That's an example of what we're talking about here. If it's an even coefficient, if it's an even degree, but the leading coefficient is negative. So think about what that's going to do. Even, sameness, still going to be the same. Their behavior is going to be the same on both sides. Why did this stop recording? Okay, if the degree is even and the leading coefficient is negative, same idea, even, sameness again, that's how I remember it. It's going to do the same thing, but instead of rising on the left and rising on the right, it's going to do the opposite. It's going to fall on the left and fall on the right. So think about a parabola, for example, would be a degree 2, but if it had a negative a value in the front, remember we said it opens down, and that's what we're talking about. Falls on the left, falls on the right. So let's apply this a little bit. Let's take a look at an example here. It says use the leading coefficient test to determine the end behavior. So if you're ever asked about end behavior, this is how we're going to do it. So look at example A. What is the leading coefficient and what is the degree? So the degree is 3, which of course is odd. That's the highest powered term. And even if these are out of order for some reason, it doesn't matter which one's listed first. You look at the highest powered term for your degree. So that's 3, which is odd. The coefficient is the coefficient in front of that term with the highest power, so we can see that the value for A this time is 1, which is positive. So look back at your cases here. If we have a positive coefficient and an odd degree, that would be this first case right here. So it's going to fall on the left and rise on the right. You can say it in words, or you could even just draw it if you want to. Falls left, rises right, and that's good enough for me, as long as you give me the justification, giving me the degree and the leading coefficient. How about letter B? This one, it's a little bit tougher to see exactly what the degree is because this is in factored format. So what I want you to think about is if we were to multiply this out, how would we get the degree and the leading coefficient from that? I'm not going to multiply the entire thing out. All I need is the highest powered term. So let's do this. Let's just go ahead and think about if we were to FOIL this x minus 1 term. We'd have to square that before we do too much. Do you agree that we would get negative 4x to the third times x squared minus ... some terms that follow it, and then the x plus 5 is still there? I'm not even concerned with the rest of these terms. All I care about is the highest powered term, and that's going to be determined by that x squared term. Now, same thing. If I were to take that negative 4x cubed and distribute it, I would get negative 4x to the 5th power, because remember you add exponents, minus ... a bunch of terms that would follow that, times the x plus 5. And then if we were to distribute all of that, we would have negative 4x to the 5th times x. So the first term would be negative 4x to the 6th. And then we'd have a bunch of terms that would follow that if we were to multiply all of that out. But I don't really care what the rest of the terms are. All I care about is the highest powered term, because that's going to tell me the degree and the leading coefficient. So negative 4x to the 6th is the highest powered term. So the degree for that is 6, which of course is even. And the leading coefficient is negative 4, which of course is negative. So think about, look back at your 4 cases. Which one are we dealing with here? So we have an even degree and a negative coefficient. So that would be this case right here, even degree, negative coefficient. So it's going to fall on the left and fall on the right. And again, you could say it in words or you could just draw it. That would be fine with me. All right, so let's take a look at example 2. Example 2 is asking us to find the zeros of this polynomial and something called the multiplicity of each. So if you remember back to chapter 1, we talked about how to solve polynomial equations. And one way to solve those was to factor everything and use the zero product property. So remember the zero product property was we set the equation equal to 0. And by the way, I need to point something out here. I asked you to find the zeros of this polynomial. We need to be clear on what we mean by zeros. Zeros is another name for x-intercepts. Sometimes books will call these roots. That's another term. I might use them interchangeably, but x-intercepts are what we're usually calling them. Zeros, same thing. So remember how you find x-intercepts of any function. This is an important concept I want you to remember throughout this entire class, is that anytime you're asked to find the x-intercepts, we set the y equal to 0. We put in 0 for the y and we solve. Remember, g of x is the same as y, so I'm going to replace that with a 0 and I'm going to solve. Now, the zero product property says once this is equal to 0, we can set each individual factor equal to 0. So I'm going to set x minus 5 equal to 0. X plus 2, oh, this was x plus 2 squared. I forgot the square, so make sure you include that. So we have x plus 2 squared equal to 0. And then we have x minus 1/4 to the 4th power equal to 0. So we have everything set equal to 0, and let's solve individually. So the first one, I'm going to add 5 to the other side, so I get x equals 5 as one of my zeros. The next one, we have x plus 2 squared. Now, I could think about, using the square root method to solve this. Take the square root of both sides. I get x plus 2 equals, well, what's the square root of 0? It's still 0. So my 0, or my x-intercept there, is x equals -2. And then the last little equation can be solved similarly. Instead of taking the square root of both sides, we're going to take the 4th root of both sides. So that just leaves me with x minus 1/4 equals, well, 4th root of 0, that's just 0. So we get x equals 1/4 for that last solution. Now let's talk about the multiplicity. So the multiplicity, there's some use to it when we go to graph, and we'll talk about that in a few minutes. But right now, all I want you to remember is the multiplicity can be found by looking at the power on each of the factors where those zeros came from. So in other words, x minus 5, that's raised to the first power in the original equation there. So the multiplicity that goes with that would be 1. How about the x equals -2? What was the power or the exponent on the factor that came from? X plus 2 was the factor. The power on that was 2. So the multiplicity for that 0 would be 2. Each individual x-intercept has its own multiplicity. How about the last one? We have x equals 1/4. Look back at the factor that came from. It came from the x minus 1/4 raised to the 4th power. So what would the multiplicity for that x-intercept be? And that would be 4 because of the exponent that it came from for that factor. Let's do another one. Let's look at example 3. This time we have to actually do some factoring ourselves. So the idea is the same. We're going to set this equal to 0, but we have to factor this. Do you remember how to factor when we have 4 terms? And hopefully you're thinking 4 terms, the only way to factor that is to use group factoring. So I'm going to group the first 2 terms, and I'm going to group the second 2 terms. So the first 2 terms, the GCF with those 2 terms is just x squared. So I'm going to factor out x squared, and what would I multiply that by to get x cubed? That would just be x. What would I multiply that by to get 3x squared? That would just be 3. Pause for a minute, make sure you see what I did. I factored x squared out of those first 2 terms, and that left me with x plus 3 in parentheses. The second 2 terms, you notice that that third term was negative. I always keep the negative with that third term if it's negative. And then when I go to factor, I take the negative out. And then is there any other GCF between x and 3? No, there's not. So I'm just going to put a 1 there. So it's like taking out a -1. And then what does that leave you with in the parentheses? So -1 times what gives you -x? That would just be x. -1 times what would give you -3? Well, that would have to be +3. And remember, when you group factor, what's in the parentheses has to match. Okay, so now what's in the parentheses matches. So I think I've group factored this correctly. So remember, we factor out the common factor, the x plus 3. And that leaves me with x squared minus 1. And then x squared minus 1 is a difference of squares. So I think it's best when you do these to go ahead and factor completely. So we have x plus 3 still, and then the x squared minus 1, that's a difference of squares. So that'll be x plus 1 times x minus 1. Now the zero product property says to find the zeros. I'm going to set each of these factors equal to 0 on its own. So we get x plus 3 equal to 0, x plus 1 equal to 0, and x minus 1 equal to 0. So in the first expression, I get x equals -3. In the second expression, I get x equals -1. And in the third expression, I get x equals +1. Now, what is the multiplicity for each of those? Go back to the completely factored version of your expression, and that was right here, x plus 3. The power on that was just a 1, so it has a multiplicity of 1. X plus 1, the power on that was just a 1 as well, so that has a multiplicity of 1. And then x minus 1, again, that's a power of 1, so that also has a multiplicity of 1. So they all have a multiplicity of 1. Let's try example 4. It's the same question, but again, we have to do the factoring. So I'm going to set the equation equal to 0. We have a trinomial here, and hopefully you see that it's got a GCF. What is the GCF that I can take out of all three of these terms? They all have x in common, and the lowest power was x squared. So I'm going to take out x squared, and when that leading coefficient is negative, I usually just take that negative out with it because it's easier to factor what's left on the inside without the leading coefficient being negative. So if I take out a negative x squared, what would I multiply that by to get negative x to the 4th? And that would just be x squared. And then what would I multiply negative x squared by to get positive 4x cubed? So that would be a negative 4x. And then what would I multiply negative x squared by to get negative 4x squared? That would just be positive 4. Now, hopefully this will factor further. I don't think you'll have any in the homework that don't completely factor. And this does factor a little bit further if you look at it. I'm going to bring down the GCF. And we're looking for two numbers. We have a trinomial here, so we're looking for two numbers that multiply to 4 but add to negative 4. So I'm going to make my two parentheses. I know the first two terms have to be x and x. So what two numbers would multiply to positive 4 but add to negative 4? Well, it's got to multiply to a positive, which means the signs have to be the same. And it's got to add to a negative, so that means they both have to be negative. So factors of 4 would have to be 2 and 2. So we've got it completely factored. Now, do you notice there's a shorter way we could write this x minus 2, x minus 2? And just to help us with the multiplicity, I'm going to shorten it up and write it as x minus 2 to the 2nd power. Make sure you see that. You don't have to write that step out, as long as you see that there are two x minus 2 factors. So when I write the multiplicity for the 0 that comes from that factor, I need to consider both of those factors. Let me show you what I mean. Let's get the zeros. So let's take the negative x squared. We have to set that equal to 0. Divide by negative 1. We get x squared equals 0. We just get x equals 0. What is the multiplicity of that, though? We have to look at the x squared that it came from. Since that's a second degree, that means the multiplicity for that would be 2. How about over here, x minus 2 squared? If we set that equal to 0, square root both sides, we get x minus 2 equals 0, so we get x equals 2, but the multiplicity is what? It's going to be 2 because we had x minus 2 squared, or if you noticed earlier, we had x minus 2 times x minus 2. We had two factors of that, so therefore the multiplicity is 2. One other trick with multiplicities that might help you see what's going on is when you're done, all of your multiplicities should add up to whatever the original degree was for the polynomial. So like this was a 4th degree polynomial. Do your multiplicities add up to 4? Well, multiplicity of 2 and multiplicity of 2, that adds up to 4. In the last example, what degree did we have? So we had a degree 3 in the last example. And you notice that your multiplicities 1 plus 1 plus 1 adds up to 3. So that's how you know you've done your multiplicities correctly. All right, so what's another name for zeros of a function? We said that could also be called x-intercepts. And you may also hear me refer to it as roots, same thing. What's the significance of that on the graph? The x-intercepts are where the graph touches the x-axis. So when we go to sketch the graphs of these, this is how we're going to know where things end up, is based on what those x-intercepts are, because that's where the graph will touch the x-axis. So why is the multiplicity important? Well, here's where the multiplicity is really going to help us out. When we go to make a sketch of the graph, if the multiplicity at a particular 0 is odd, then the graph will cross the x-axis at that x-intercept. If the multiplicity of a 0 is even, then the graph will touch and turn around at the x-intercept. So touch and turn around on the x-axis. Sometimes I say it bounces. Oops, the x-axis. It bounces at that location, but our book calls it touching it and turning around. So we'll do an example. You'll see what I'm talking about. One more important point before we start graphing these is to look at the number of turning points. Turning points are your relative, remember in chapter 2 we talked about relative max and relative minimum. Those are also your turning points. And so the max number of turning points a polynomial of degree n can have is n minus 1. And we're going to use that to just help us make sure we've done our graph correctly.